Hi, hello dear students. Hope you are following my classes. Anyway, welcome to my second lecture on solid state. Here in this lecture, I would like to continue my transforming information regarding solid states of chemistry, particularly the classification of solids. As we said earlier in the first class, we discussed about different kinds of ideas which are initiated in the classification of solids into crystalline solids and amorphous solids. Earlier we are told that amorphous substances have very low or short range ordered constant particles, but whereas the most of actually the solid substances in the nature are said to be available in crystalline nature, crystalline in manner. That means substances we used to call crystalline substances, most of the substances in nature. That's why crystals can also be classified how they classified in the nature, depending on the binding forces. I can say the forces which are existed between the constant particles in the crystalline solids, binding forces, or we can also call their intermolecular forces, inter-attractive forces, interparticle attractive forces. So depending on that type of binding forces, these crystalline substances like iron, copper, silver, and even non-metallic materials like sulfur, phosphorus, iodine, and such type of compounds we have. Solid sodium chloride is the best example, and salts like zinc sulfide, and naphthalene, organic materials like naphthalene and crystalline solids are there. And these crystalline solids, how they are going to be observed and what kind of crystalline solid that is most important in our discussion. That also will be discussed in this present session. That is nothing but the classification of crystalline solids in terms of the intermolecular forces operating between the atomic constant particles. So that is, the concept is nothing but classification of crystalline solids. Classification of crystalline solids, and particularly this is on the basis of intermolecular forces operating in them. When you're talking about such kind of interesting things, you have to just recollect a small information which we have already studied in our lower class 11, states of matter, and that is particularly that small concept is called as intermolecular forces. Intermolecular forces. In such a kind of discussion in the previous classes, we have given valuable information regarding the intermolecular forces into dispersion forces. Dispersion forces are London forces. Dipole forces. Okay. Not only that one, Coulombic force of attractions, hydrogen bond-like forces. Such kind of different things elaborated in our lower class. in a previous session also, particularly intermolecular forces, a series of sessions we have conducted. In that also we have given most important extension of that dipole forces in like that, dispersion forces or London forces, usually we will call it as induced dipole forces, Coulombic or strong electrostatic forces of attractions between dipole, even hydrogen bond like forces. When talking about bonds in chemistry, definitely this classification is also called as the classification on the basis of the type of the chemical bond existed in the between the constant particles in solids. That is also another kind of thing we can say here. The classification on the basis of intermolecular forces or classification on the basis of bond type between the constant particles in the crystalline solids we can call. So this is on the basis of bond type. On the basis of bond type also we can call. So when we start discussing about this classification, that means crystalline solids classification on the basis of nature of intermolecular forces operating in them, there are four types are there. Major important things according to the bond type we have molecular. The one is called as molecular. The one is called as ionic. The other one is called as covalent hydrogen bond. So mainly the bond type is of molecular, ionic, covalent. Usually we call in the subcategory of covalent we have hydrogen bond, hydrogen bonding like forces. Molecular solids, ionic solids, covalent solids, hydrogen bond like solids. Even when you are talking about covalent bonds and all, this will come, and particularly some cases we will call extension metallic bonds also we will discuss. Like this kind of different ideas are useful in the classification of crystalline solids. First of all, when we talking about molecular solids, the first classification I can say that is molecular solids. Molecular solids. It is a separate information in the classification of solids, and study about the molecular solids is again broadly divided into three important major portions depending on the nature of the intermolecular force existed between the constant particles. One kind of molecular solid is called as non-polar molecular solids. Non-polar molecular solids. That means in the molecular solids classification, non-polar molecular solids. So what is this one? How can we understand this molecular solid? Means the key point here, which is nothing but the dispersion forces. What is the force existing between the particles in this kind of non-polar molecular solids is nothing but there is a kind of attractive forces. They are nothing but dispersion forces or London forces. Non-polar molecular solids existed with dispersion dispersion forces, also called as London forces. Usually we will say there is a induced dipole informations in the intermolecular forces concept we have studied. That is nothing but the dispersive forces or London forces. The second type of important classification of the subclassification of this molecular solids is polar molecular solids. Polar molecular solids. Polar molecular solids, in the name itself it is very clear that the given species must be having polarity, that means charged species. So these are polar molecular solids. Usually they are going to be operated using dipole forces. What is the type of force? Dipole interactions. Dipole interactions. Dipole interactions are actually responsible for generation of this kind of molecular solids called polar molecular solids. This is the second one. Coming to the third and most important one, here already we have discussed in this subclassification, that is hydrogen bond-like forces, hydrogen bonded molecular forces. Hydrogen bonded molecular solids. Hydrogen bonded molecular solids. Second one is polar molecular solids. First one is non-polar molecular solids. Okay. So non-polar molecular solids, polar molecular solids, hydrogen bonded molecular solids. Directly we are specifying hydrogen bond. Hydrogen bonded molecular solids means definitely there exists a strong hydrogen bonds which binds the molecules of this kind of crystalline solids, and usually water is a best example, H2 is a best example. We will call that one is ice in this category. Okay. This is actually major classification, subclassification of this kind of molecular solids. So what are molecular solids? Molecular solids are nothing but crystalline solids classification in which constant particles are nothing but molecules. What are the constant particles? Molecules. And in that, small molecules, except there are some noble gases are there, we know. Noble gases like xenon and all, where the units are actually there in the atoms are there in units there. The other cases all we have, suppose if you take hydrogen, if you take chlorine, iodine, at room temperature they may be liquid state and gaseous state, but in cold conditions they are molecular solids. Such kind of solids are said to be held together by the specified intermolecular force. Here is nothing but dispersive forces or London forces in the case of non-polar molecular solids. Okay, and this is said to be the most important step in the observation when you observing some substances. Okay, and those substances like solid substances, particularly carbon dioxide, if you take carbon dioxide, actually in solid state it is called as dry ice. If you take H2O, ice, this is ice. Similar fashion, if you take another example, if you take some other example like NH3, ammonia which is in solid state, iodine, solid iodine. If you consider all these things, you will be getting a small confusion also. Why? Because they are going to start giving different kinds of examples like this. They may be giving a hydrogen, chlorine, iodine, or they may give solid SO2, NH3, solid NH3, or they may give the like this H2O, even hydrogen fluoride, HF, in solid state, they may give like this, or so many examples they may start giving in this kind of discussion. Some may be belonging to particular classifications. Okay, suppose let us see, it is CO2, dry ice. What is that? CO2, or we can call this is dry ice. What is this dry ice? This comes under molecular solid. Okay, dry ice will comes under molecular solid. But when you are talking about the molecular solids, these examples belongs to which type of molecular solid is definitely a question arises. So you must understand, if any kind of weak van der Waals forces or hydrogen bond like forces are there in the given examples, they belongs to hydrogen bonded molecular solids. And if you identify that the molecules are non-polar molecules and they will start becoming induced dipoles because of the unsymmetrical arrangement of electrons around the molecules, that means the situation arises like that when the molecules come closer, tiny molecules is all, when they come closer, they will become induced dipoles. Such cases, London forces will be operated and those molecules will belongs to, those examples will belongs to this non-polar molecular solids. And some of the examples, like we have hydrochloric acid, HCl in solid state, sulfur dioxide in solid state. These examples will comes under, ammonia also will comes under polar molecular solids. So this will comes under polar molecular solids. This will comes under hydrogen bonded molecular solids. And H2Cl2, I2, all this will comes under non-polar molecular solids. So polarity, non-polarity, depending on the dipole moment also we can understand, and that is from the chemical bonding. Again we can see how it is possible to tell about the polarity, non-polarity, symmetry, unsymmetry, and all these things. Okay, so this is the type of classification we have. Again, with a questionnaire also we can understand this type of molecular solids and their classification. Okay. Now, let us broadly discuss about these things. That means the first category, molecular solids, we have discussed. In that solid carbon dioxide, dry ice, sugar, iodine, even naphthalene, this all comes under some examples of this molecular solids. Let us see what is the second type. I am going to just tell about ionic solids in this category. Ionic solids. When you are talking about solids, ionic solids, specifically you mentioned that the type of chemical bond or intermolecular attractive force is Coulombic force of attraction or electrostatic force of attraction between oppositely charged ions. So oppositely charged ions means, you know, cations and anions, they are said to be held together by strong Coulombic forces or electrostatic forces of attraction in this kind of the crystalline solids. So ionic solids are nothing but the crystalline solids in which ions are the most important constant particles in this one. Constant units are ions in this category. Such kind of ionic solids are actually formed by three-dimensional arrangements of cations and anions. And these solids, actually these are hard materials compared to molecular solids. Why? Because in molecular solids what will happen? The hardness will be very less. That means they are very soft. And even their melting points and all very low. Less than 300 Kelvin will be there. Even at 273, above 273, below 300 Kelvin, these molecular solids will exist, and they are insulators. They are bad conductors of heat and electricity. But ionic solids are quite different. In solid state, these are also bad conductors of heat and electricity. But in the molten state, they are good conductors of the good electric conductors. Why? Because the ions will definitely be in a under movement in the molten state. Ions will be not static, not dynamic in the case of solid state. Ions will be dynamic. That means they will start moving from one place to another place. That means free moving ions will be noticed when the ionic solids are dissolved in water, or molten state also we can consider. So that is the major difference between the ionic solids and molecular solids. When you come to talk about the melting points, here very low, here very high. So what are ionic solids? Ions are the most important constant particles. And what are the forces? The forces are nothing but strong electrostatic forces. Strong electrostatic forces. Even you can also call they are Coulombic forces. Operated or operating between ions, cations and anions. These are constant particles. Which are constant particles? Cations and anions. Cations and anions. So, taking very best example and easy example for understanding, that is sodium chloride. You know, its melting point is very high melting point. That means high melting point, even boiling points also high values. The reason behind that one is we are telling they are strong electrostatic forces. Okay, the strong electrostatic forces will give high melting points, high boiling points to this kind of solids, ionic solids. Ions are actually not free to move in solid state. That is why they are insulators, electrically insulators in solid state. But what is the important point we discussed in this one is they are good conductors of electricity when they are in molten state or liquid state. So they are electrically or electrical insulators in which state? Solid state. Reason, the ions are not free to move. Solid state meaning here is nothing but ions are not free to move. Whereas these are good conductors of electricity. As I said earlier, definitely conduct electricity. They will conduct electricity In which state? Either molten state or in the dissolved water state. Molten state or in when they dissolved in water. So this is the most common question usually they will ask in the examination, particularly in the case of ionic solids. Okay. So ionic solids is the second category we have discussed. The first we have discussed about molecular solids. Next we have discussed about ionic solids. Molecular solids and ionic solids. Let us talk about the next thing. Third one, I would like to talk about metallic solids now. The third category, metallic solids. Metallic solids. Here also in the name itself, we are talking about metallic bonds. That means the type of chemical bond which is holding the metal atoms. When the metal releases electrons, again that electrons will bind the positively charged metals or the metal atoms. So that we will call it as metallic bond. Metals, usually they will be positively charged as they lose electrons. After losing electrons, and that metal ions will be present in a sea of electrons, the free electrons, and those free electrons again binds the metal atoms or positively charged metal ions called as metallic bond. So metallic bond is the basic understanding in chemical bonding. We have talking about free electron theory, Lorentz-Drude theory, that is giving clear idea about how can we understand the metal atoms are bounded by electrons. So one electron is negative, metal ion is positive, but the two metal ions will be joined because of these electrons, because metallic bond is the reason for that. So that electrons definitely called as mobile electrons. They will spread out throughout the crystal, and that will definitely responsible for this electrical conductivity of metallic solids. Okay. So what are the main things in this one is nothing but in metallic solids the constant units are nothing but metallic solids are nothing but positively charged ions. Positively charged metallic ions bonded by free electrons around them. So that is the metallic bond concept, metallic solid concept. So the positively charged metal ions are definitely held together by free moving electrons, and definitely they will change the entire property of the crystalline solids, the metallic crystalline solids, and definitely all the electrons will grouping together and making the metal atoms come close together to form this metallic crystalline solids. And coming to the heat application, when we heat this kind of crystalline solids, what will happen? Thermal conductivity, how it will be there, means high thermal conductivity will be there, high electrical conductivity also will be there in this case compared to the others, the molecular solids and ionic solids we have discussed earlier. So heat is applied. When we apply heat, what will happens? One portion to another portion, this thermal energy will be uniformly spread out in the case of metallic solids, because electrons are said to be free electrons, free moving electrons in this one. That is the important characteristic. Not only that one, the major important characteristic of this metallic solids is nothing but they are shining in nature. That means metallic solids are having luster, and some metallic solids, crystalline solids exhibit certain colors also in some cases of application of heat. Also due to the presence of free electrons only it is all possible. And finally they are malleable and ductile also. But ionic solids are there, they are hard and brittle, and here in the metallic solids they are malleable and ductile. So we can make wires and we can make sheets with the help of this metallic crystalline solids. So metallic crystalline solids, when you are talking about metallic crystalline solids in domestic life also, we used to discuss about copper wires. Copper is the best example. Silver, gold, aluminium, even we have sodium is also useful in the discussion of metallic solids. Okay, so metallic solids are malleable and ductileable. So malleable and ductile means the meaning here is nothing but we can make wires, we can make sheets with the help of this metallic solids. So here also an orderly arrangement of metal ions because of the free electrons which are present in between the metal ions. So that is the third one. Most important one, now we are going to see, that is the fourth one, covalent solids. Even we can also call their network solids. Covalent or network solids. Covalent or network solids. In the name itself we are mentioning they are covalent. Covalent means covalent bond is responsible in the development of this kind of solids. That means in these solids the constant particles nothing but they are atoms, okay, held together by covalent bonds, strong covalent bonds, not only weak bonds, they are strong covalent bonds. So wide variety of crystalline solids, anybody ask the wide variety of crystalline solids, actually they comes under this category, that is covalent or network solids. They are all formed with the help of covalent bonds between the adjacent atoms in this crystal. Actually these are giant molecules. When we are talking about giant molecules, just recollect the information from our lower study about graphite and diamond. Graphite and diamond, they are giant molecules. They are allotropes of carbon, and that graphite and diamond or solids comes under this category. That means covalent bonds are present between the carbon atoms in graphite and diamond, and the covalent bonds, strong covalent bonds, and particularly they are directional in nature. Ionic bonds are not directional in nature, non-directional. Covalent bonds are directional. So that directional covalent bonds are strong covalent bonds in the development of network solids. Most important, and number of crystalline solids existed in this category. We all know that covalent bonds are strong and directional. That's why these atoms are held very strong at their positions. In this case of covalent or network solids. Talking about many things about this type of solids, they are hard and brittle like ionic solids also. But when compared to all the types of crystalline solids, this type of solids exhibits highest melting points because of strong directional covalent bonds between the atoms. So they have extremely high melting points, even decompose before melting points also. Some are decomposed before the melting points. They are nothing but giant molecules. Insulators. The one word used here, insulators, is nothing but they don't conduct electricity. Do not conduct electricity. Only we have metallic conductors, metallic solids. They conduct, they are good conductors of electricity. Even ionic solids, when they are in molten state, they are good conductors of electricity. But these covalent or network solids, they are bad conductors of electricity. Best example we have diamond. We have best example diamond. Even we have silicon carbide. Silicon carbide is also a typical example for this type of covalent bond or network crystalline solid. And when it comes to exceptional case in this one is graphite. When you see graphite, it is soft and it is a good conductor of electricity. Reason behind that one is electrons in the structure, graphite layered structure, the electrons will move in between the layers. That makes graphite lubricant and soft in nature, and also an exceptional property when compared to diamond. The graphite we have observed. Whereas that structure of graphite and layer structure is studied in the first year syllabus we have. They are three-dimensional and graphite is a layered structure. Layered structure. Because of this layered structure, this graphite is a good conductor of electricity. And why graphite is good conductor of electricity? We can see the structure of graphite, and from the structure of graphite we can understand why graphite is good conductor of electricity compared to diamond. Diamond is a bad conductor of electricity. There won't be any kind of pi electrons roaming in between the structure between the atoms. So there is no such kind of observation in case of diamond, and silicon carbide used in bulletproof manufacturing is not observed. But in this case, it is observed. So three-dimensional and strong directional covalent bond is responsible for the development of this network solids. So this is about the classification of crystalline solids on the basis of bond type, on the basis of intermolecular forces operating between the constant particles, which was noticed. Okay. In the next coming session, we will be having questionnaire. That means we will discuss what kind of the questions will be asked from these classification of solids. In the next session, we will take up regarding all kinds of classifications. We will discuss question, answer, discussion on the classification. After that, we will further go forward in the solid state with different kinds of ideas. Thank you very much.